This podcast is brought to you by the mystical oracle of random sampling. Forget crystal balls. Our sacred task begins with conjuring a truly representative miniature universe from the sprawling cosmos of a population. With digital algorithms as our magic wands and statistical formulas as our ancient incantations, we carefully select the chosen few, a handful of individuals who will, against all odds, perfectly mirror the vast, diverse sentiments of millions. It's a breathtaking act of statistical sorcery attempting to contain the world in a teacup.
Welcome back to the Deep Dive as we continue our journey through survey research.
It's great to be back. In our last episode, we got really granular on instrument design, how to meticulously craft the questions themselves to get valid and reliable data. We treated the questionnaire like a precision instrument.
We did. We talked about avoiding leading language, the pros and cons of different scales, and how to structure a questionnaire logically. But as we know all too well in the lab, having a perfectly calibrated instrument is only half the battle. If you put a humanized sample on your top-of-line chemistry analyzer, your potassium result is still garbage.
That is a perfect analogy, and it's the same with research. A flawless set of questions, our instrument, is useless if you point it at the wrong group of people. Your pre-analytical phase has to be solid. So today, we're tackling that critical next step. How do you select your sample? We're moving from designing the tool to collecting the specimen.
We're talking about sampling strategies and data collection. Our plan is first to talk about the absolute basics, why we sample people in the first place. Then we'll get into the nitty-gritty of sampling strategies. We'll cover the gold standard probability methods that allow for true generalization, and then the more practical non-probability methods that we often have to use in the real world.
After that, we'll tackle the million-dollar question, how many people do you actually need to survey? We'll demystify the concept of sample size. And finally, we'll walk through the different ways to actually administer the survey, online, by mail, over the phone, and the pros and cons of each.
It's a journey from a research question all the way to a high-quality dataset. So let's get started. To understand how to sample, we first need to appreciate why we sample. What's the fundamental idea here?
It all comes down to a simple challenge. We want to know something about a large group of people, but we can't possibly ask every single one of them. Imagine your hospital system wants to know what all of its thousands of nurses think about the lab's turnaround time for stat troponins. Contacting every single nurse would be a logistical and financial nightmare. This is where sampling becomes essential.
This brings us to two critical terms we need to define right away: the population and the sample. I think this is where our lab background gives us a real head start.
I completely agree. We do this every day. The population is the entire group you're interested in. It's all the nurses in the hospital system. In the lab, the population is all the blood circulating in a patient's body. You want to know the patient's true hemoglobin, but you can't test all 5 liters of their blood.
So you take a sample, a small, manageable subset of that population. In our survey, that might be 200 nurses selected from across the hospital. In the lab, it's the 4 milliliters of whole blood you draw into a lavender top tube. The entire science of survey research, and phlebotomy for that matter, is built on one crucial assumption: that the sample is representative of the population.
That's the key word, representative. We trust that the hemoglobin in that tube of blood accurately reflects the hemoglobin in the patient's entire circulatory system. Likewise, a good survey sample should ensure that the opinions of the 200 nurses we survey accurately reflect the opinions of all the nurses. If our sample isn't representative, we say it's biased, and the conclusions we draw will be flawed.
Beyond just being practical, a good sample can sometimes be more accurate than a full census, which is trying to survey everyone. How does that work?
It seems counterintuitive, doesn't it? But think about a massive census project. It's so huge that it's prone to errors. People don't respond, data gets entered incorrectly, staff aren't trained well, and people get respondent fatigue. By focusing your resources, your time, money, and energy on a smaller, well-selected sample, you can do a much better job. You can follow up with non-responders, carefully check the data, and ensure higher quality control over the whole process. It's quality over quantity.
That makes perfect sense. It's like running a tight, well-controlled QC protocol versus just mindlessly running thousands of patient samples without checking if the instrument is even in calibration. The controlled, smaller data set is infinitely more trustworthy.
Exactly. So now that we're sold on the why, let's get into the how. The methods we use to select our sample are broadly divided into two categories: probability sampling and non-probability sampling. Let's start with the gold standard, probability sampling.
Right. If this were a CLIA inspection, probability sampling is what the inspectors want to see. What's its defining feature?
The defining feature is random selection. In a probability sample, every single individual in the population has a known, non-zero chance of being selected. This is huge. Because of this randomness, we can use statistics to estimate how closely our sample results reflect the whole population, complete with a margin of error. It's what allows us to say something like, we are 95% confident that the true satisfaction rate in the population is between 45% and 55%. It's our shield against selection bias.
Okay, so let's break down the main types. The most basic one sounds like its name. Simple random sampling.
It's the purest form. Conceptually, it's like putting everyone's name in a giant hat and drawing a few. To do it properly, you need a sampling frame, a complete list of every single person in your population. So if our population is all MLS staff in our lab, we'd get an employee roster from HR, then we'd use random number generator in Excel or another program to pick, say, 30 names from that list. Every person has an equal shot.
The strength is obvious. It's the most unbiased method if done right. But I can see the weakness immediately. Getting that complete list, the sampling frame, can be really hard or even impossible for large populations. You're not going to get a complete list of every patient who has ever had a CBC done at our facility.
Precisely, that's a major hurdle. So a slightly more practical method is systematic sampling. This offers a bit of a shortcut. Here, you still need a list, but instead of random numbers, you select people at a regular interval.
How does that work?
Well, you first calculate your sampling interval. You divide your population size by your desired sample size. Let's say we have 500 phlebotomists in our system, and we want to survey 50. Our interval is 500 divided by 50, which is 10. Then you picked a random starting point between 1 and 10. Let's say you start with the third person on the list. From there, you just select every 10th person, person number 3, person 13, person 23, and so on until you have your 50.
That seems much easier to execute than generating 50 different random numbers. But a potential pitfall is called periodicity bias. That sounds like something we would see in time series QC data.
It's the exact same concept. It happens if there's a hidden cyclical pattern in your list that lines up with your interval. Imagine a list of samples received in the lab is organized by time, and every 20th sample is a routine QC specimen. If your sampling interval happened to be 20, you could end up with a sample of only QC specimens or no QC specimens. Your sample will be horribly biased. You have to make sure your list is randomly ordered or doesn't have a hidden pattern.
Okay, that's a great lab analogy. Now, what if our population has important subgroups we need to make sure we capture? For instance, if we're surveying the lab, we can't just talk to the day shift. We need to hear from the evening and night shifts too.
You've just described the perfect use case for stratified sampling. This is an incredibly powerful technique. You first divide your population into distinct, non-overlapping subgroups, which are called strata. Your strata could be shifts like day, evening, night, departments, chemistry, hematology, microbiology, or experience level, 1 to 5 years, 6 to 10 years, 10 plus years.
So you create these buckets first, then what?
Then you perform a simple random or systematic sample within each bucket. This guarantees that you will have a representative number of people from every single subgroup you care about. You can sample proportionally, so if 60% of your staff is on day shift, 60% of your sample comes from day shift. Or you can even oversample smaller groups like the night shift to make sure you have enough of their responses to do meaningful analysis.
This is fantastic. It's like ensuring our QC plan includes low, normal, and high controls. We don't just test the normal range. We need to verify performance across the entire reportable range. Stratified sampling lets us do that for opinions.
Perfect analogy. The last probability method we'll cover is a lifesaver for logistics, cluster sampling. This is for when your population is geographically spread out. Imagine a national reference lab wanting to survey its phlebotomists who work in 200 different patient service centers across the country.
Visiting all 200 centers would be impossible.
Exactly. So with cluster sampling, you don't create a list of people, you create a list of clusters, in this case, the 200 service centers. You then randomly select a sample of, say, 15 centers. And here's the key. You then survey every single phlebotomist within those 15 chosen centers.
So you randomly sample the groups, not the individuals directly. I can see how that saves a ton of travel and money, but what's the catch?
The catch is a higher sampling error. People within a cluster tend to be more similar to each other than people in other clusters. The phlebotomists at the center in Miami might have very different experiences and opinions than the ones in Minneapolis. This homogeneity within clusters can make your overall sample a bit less diverse than one from a simple random sample. It's a trade-off between cost-effectiveness and statistical precision.
Okay, that makes sense. So simple random, systematic, stratified, and cluster. Those are our gold standard probability methods. But in the fast-paced, often resource-strapped environment of a hospital lab, we don't always have the time or the perfect lists to do these. This brings us to non-probability sampling.
This is the reality of a lot of research. The defining feature of non-probability sampling is that selection is not random. The probability of any one person being chosen is unknown. Because of this, you lose the ability to statistically generalize to the whole population with a known margin of error. The risk of bias is much, much higher.
So why would we ever use these methods?
Because they are practical, fast, and cheap. They are invaluable for exploratory work, pilot testing a survey, or when you're studying a very specific, hard-to-reach group. The most common and, let's be honest, most abused method is convenience sampling.
This is just grabbing whoever is easiest to access, surveying the students in your class or the first 10 people you bump into in the cafeteria.
Exactly, or the lab manager sending a survey link only to the day shift heme team because they're the easiest to reach. It's incredibly biased. You're missing everyone else. But it has a legitimate use for pilot testing. Before you do a big, expensive survey, you can give it to a small, convenient sample to see if the questions are confusing or if the survey link is broken. It's for kicking the tires.
A more sophisticated approach seems to be purposive sampling. This one sounds like it has more intention behind it.
It does. It's also called judgmental sampling because the researcher uses their judgment to select participants who have specific knowledge or experience. The goal isn't to be representative, it's to get deep insights from a targeted group. For example, if you're trying to understand the root causes of specimen labeling errors, you wouldn't survey the whole hospital. You might purposefully select a few ER nurses, a few phlebotomists, and a few lab accessioning staff who you know have direct experience with the process.
Okay, so it's about picking experts or key informants on purpose. What about a situation where you can't even find the people you want to study? Let's say you want to survey lab professionals who have left the field entirely to understand retention problems. They're not on any employee list.
That's the perfect scenario for snowball sampling or chain referral. You start by finding one or two people who fit your criteria, say through a LinkedIn group for former laboratory scientists. After you interview them, you ask the crucial question, do you know anyone else like you I could talk to? They give you a few names, you contact those people, and your sample snowballs. It's essential for studying hidden or dispersed populations. The obvious limitation is that your sample will be very homogeneous. Everyone tends to know each other.
Right, you're not getting a very diverse set of experiences. Two other sampling techniques to mention are quota sampling and voluntary response sampling. Quota sampling sounds a lot like stratified sampling. What's the difference?
It's the non-probability version of stratified sampling. Like with stratified, first you identify key subgroups and their proportions in the population. For instance, our lab is 50% MLS, 30% MLT, and 20% phlebotomists. You then set a quota to match this. I need to survey 10 MLSs, 6 MLTs, and 4 phlebotomists. The crucial difference is how you fill those quotas. Instead of random selection, you use convenience sampling. You just grab people until your buckets are full. So while the final numbers look representative, the selection within each group is biased.
Finally, voluntary response sampling. This one seems to be everywhere.
It is. This is the online poll, the call-in TV survey, or the QR code on the back of your cafeteria receipt asking for feedback. The researcher puts an invitation out to the world, and people choose to participate. This is probably the most dangerous type of sample because it is profoundly biased. The only people who respond are the ones who feel very strongly, usually negatively, about the topic. You get the extremes, not the average person. The data is almost meaningless for drawing broad conclusions.
A really important warning. Okay, so we've chosen our sampling strategy. We've decided if we're going for the gold standard probability method or a more practical non-probability one. Now we hit that big, intimidating question. How many people do we need? How do we determine our sample size?
This is a blend of art and science. Before we even get to the statistics, we have to start with the practical considerations. The biggest one is almost always budget and resources. You might want to survey 1,000 people, but if you only have $100 for gift card incentives and a week to do it, that's going to be your primary limiting factor.
You also have to think about the response rate. You're never going to get 100% of people to reply. So you have to work backward. If I need 200 completed surveys and I expect only a 20% response rate from an email invitation, I need to invite at least 1,000 people to begin with.
Absolutely. And another key factor is your analysis plan. If you plan to slice and dice your data, for example, you want to compare the opinions of hematology laboratory scientists versus chemistry laboratory scientists, you need to make sure you have enough people in each of those subgroups to make a meaningful comparison.
Okay, those are the real-world constraints, but let's talk about the statistical side, the concept of statistical power, which sounds intimidating. Can you break that down?
Of course. Statistical power is the probability that your study will detect an effect or a difference if one truly exists. For analogy, consider a microscope. A low-power study is like using a blurry microscope. The thing you're looking for might be there, but your instrument isn't sensitive enough to see it. A high-power study is a sharp, focused microscope that gives you a much better chance of finding a real result.
So if we are surveying nurses to see if a new collection tube actually reduces hemolysis rates, a low-power study might miss a small but real improvement, leading us to falsely conclude the new tube is no better.
Exactly right. And a formal power analysis involves 4 key ingredients that all trade off against each other. The first, and the one that we can control most easily, is sample size. All else being equal, a larger sample size gives you more power. More data provides a clearer, more stable picture.
What's the second ingredient?
Effect size. This is the magnitude of the difference you expect to find. A big dramatic effect, like a new lab policy that cuts turnaround times in half, is easy to spot and requires a smaller sample. A small, subtle effect, like a tiny improvement in clinician satisfaction, is much harder to detect and requires a much larger sample to find it reliably.
Okay, then there's the significance level, or alpha, which we know as our p-value threshold, usually p less than 0.05. How does that fit in?
This is the risk we're willing to take of making a false positive error, crying wolf and saying there's an effect when there isn't one. If we set a very strict threshold, say p less than 0.01 instead of 0.05, we're demanding a very high level of evidence. To reach that higher bar, we need more power and therefore a larger sample.
Okay, and the last piece of the puzzle is variability in the population.
Right. If the people you are surveying are all very similar in their opinions, low variability, a small sample can capture that consensus pretty well. But if opinions are all over the map, high variability, you need a much larger sample to capture that diversity and calculate a stable, meaningful average. So ultimately, choosing a sample size is a deliberate act of balancing the practical constraints with the need for enough statistical power to find a meaningful answer.
A fantastic summary. So we know why we're sampling, who we're sampling, and how many we need. The final step in this process is deciding on the mode of survey administration. How do we actually deliver the questionnaire to our participants?
This is a crucial choice that impacts everything from cost to data quality. The dominant method today is, of course, online surveys. We get these all the time, an email link from Qualtrics or SurveyMonkey. The strengths are huge. They are incredibly cheap. Data collection is super fast, and you can program complex logic, like skipping questions that aren't relevant to a respondent.
The weaknesses are also significant. The digital divide is a real thing. If you're surveying a population that includes older, retired lab staff, for example, an online-only survey might systematically exclude them. And response rates can be abysmal because it's so easy to ignore an email.
That's right, which is why the classic mail survey still has a place. Putting a paper questionnaire in someone's mailbox can reach nearly every household, overcoming that digital divide. It can also feel more anonymous for sensitive topics.
But the cons are big. It's slow, relying on the postal service, and the costs for printing and postage add up quickly. Plus, you have to keep the questionnaire very simple. Complicated skip patterns on paper are a recipe for disaster. People get confused and just stop filling it out.
This is where having an interviewer can help, which brings us to telephone interviews. This is where the interviewer calls participants and reads the questions over the phone. A huge advantage is that the interviewer can clarify confusing questions and probe for more complete answers, which can really improve data quality.
But we all know the big problem here. Who answers calls from unknown numbers anymore? With caller ID and spam blockers, just reaching people is incredibly difficult. And there's a higher risk of social desirability bias, where people give the nice or correct answer to a live person rather than what they truly believe.
That bias is potentially at its peak in our final mode, which is also the gold standard for data quality, face-to-face interviews. This is where an interviewer meets the participant in person. You do this when you need the absolute highest response rate and the highest quality data, especially for long, complex topics.
The rapport an interviewer can build in person is unmatched. But I can't even imagine the cost and time involved. The thought of sending someone to personally interview 100 lab staff across 3 shifts, it's just not feasible for most internal projects. It's incredibly expensive and slow.
It is, which is why many researchers now use mixed-mode designs. You might start with a cheap email invitation, then follow up with a more expensive mail survey for those who don't respond online, and finally use telephone calls for the last few holdouts. You leverage the strengths of each mode.
So to bring this all together, we've gone on a complete journey. We started by understanding the fundamental concept of using a small sample to represent a large population, an idea that's second nature to us in the lab.
We then explored the rigorous gold standard probability sampling methods that allow us to fight bias and generalize our results, as well as the practical non-probability methods that we can use when resources are tight.
We demystified the challenge of choosing a sample size, showing how it's a balance between real-world constraints and the statistical power needed to get a trustworthy result.
And finally, we looked at the pros and cons of the different ways to actually get our survey into the hands of our participants.
It really shows that good survey research isn't just about throwing a few questions together. It's a systematic process. And for us as lab professionals, applying this level of scientific rigor to gathering data from people should feel very familiar. It enhances our ability to drive quality improvement, advocate for our colleagues, and better serve our clinicians and patients.
Well said. The next time you see a quick poll in an email, hopefully you'll have a new appreciation for the science behind it, and you'll be able to spot the difference between a convenient sample and a well-designed study. It makes you a more critical consumer of data and a better producer of it.
A great place to wrap it up. Thank you for joining us. Make sure to check out our next episode as we continue exploring survey research and the concepts of data management, quality, and ethics.
We'll see you next time.